Okay, a very good afternoon to everyone. Um, we are dealing with convexity and first order properties in this lecture. Um, let's recap where we are so far. We understood the convexity of machine learning loss functions so far, discussed them in some details, and then I had left a homework exercise which I'll start with today, which was about quasi-convexity of the negative of the Gaussian function. Then we'll move on to subgradient calculus, a notion of subgradients and so on, um, generalizing from direction vector. So let's just do this recap. Let's recap the notion of sublevel sets of convex functions. Um, so if a function f is convex, all these sublevel sets which correspond to the sets of x such that the function value is upper bounded by an alpha, these are all convex sets. Okay, was our first exposure last week as we transitioned between sets and functions and sets. Now the proof of that we dealt with in the last class. Here's the proof that L alpha f is a convex set for any alpha in f if f is convex. Okay, I hope there is no doubt here as such. We'll proceed. This was a very simple proof. However, where I left your homework with is that convex sublevel sets do not imply convex functions. And this brings in the notion of quasi-convexity. So function is called quasi-convex if all its sublevel sets are convex sets. However, every quasi-convex function is not convex. Okay. I tried to give you an example in the last class, the negative of the normal distribution. And I claim that the function is quasi-convex but not convex. So I had to do two things. I had to prove that it is not convex, and I have to prove that it is quasi-convex. Okay, I provided some hint here. And what I've tried to do is taken a simpler function. Okay, so this is one thing you have to start looking at. Okay, look at the form of the function. We have an x minus mu norm square divided by 2 sigma square. Now 2 sigma square is a constant division. Can we just start with simple x minus mu norm square? The negative should be remain. And I can also remove the scalar. So to begin with, I'll try and do away with this the scalar multiplication and the scalar division within the exponent. Okay, so this is a simpler function. So we'll deal with the we will begin with the special case. So for the special case, are the two proofs simple? Okay, so the special case is dealing with exp of a quadratic, negative of a quadratic. So one thing we can do is go to scalar calculus in the case of x being a scalar value, x n r, right? Not vector. So anyone has tried doing this? So what we are doing here is special case is, yeah, we have ignored 1 upon under root 2 pi and set sigma square to 1. And what have we done? We have applied here a property from basic calculus. That the function is convex if second derivative non-negative. So we're just looking at f dash f double dash x being less than 0. Sorry, non-negative. We're looking at it being strictly positive or greater than equal to 0. Okay, so is it? Well, you'll expand it, right? You see, to show that it is non-convex, you don't have to look at the vector, right? You can show for single dimensional case if it is not. Hmm. Then it's true. I mean, you don't expect convexity in the n dimensional case. The function is not convex in single dimensional case. We do not expect it to be convex in the multi-dimensional case as well. Okay, so that's the rationale behind simplification. Just want to make sure you understand this. Is this okay? Any questions? Yes, reposition this, yeah. Okay, so if there are no questions, let's just proceed with this proof. Okay, so special case can be for multiple reasons. This is a very valid reason here. Okay, so now f double dash x, we have this expansion. It's basically, exp of minus 2 x minus mu square. That is all fine. But what we have now outside, so the exp here is to whatever is, I mean, it's going to be always positive. But what is going to bail us out is this expression sitting here, x minus, sorry, minus of 4 minus x minus mu norm square, right? So this is less than 0 if x minus mu norm square, x minus mu square, sorry, is just single dimension. If this is greater than half, so the problem, this is the problem case. The problem case is when it becomes less than 0. The second derivative is negative if x is basically greater than mu plus 1 by square root 2, or x is less than minus mu minus 1 by square root 2. So the derivative is basically non-decreasing everywhere, or rather the second derivative is not positive everywhere. It's negative in several places. Okay, so it's negative for, in fact, very large range. It's positive only when when x is between mu plus square root by 2 and mu minus mu minus 1 upon square root 2. Okay, so this is not convex. But now we want to prove the second part, that it is quasi-convex. Anyone has made any effort on that?
Sir, I had a parallel question here.
Yeah, please.
So here we show that the function is not convex everywhere, but it is quasi-convex. That's what we show. But like that, I even thought like log x and all that's not convex anywhere, and still that's quasi-convex. So what is there no
Log x,
relation?
log x.
Log x is that is quasi-convex, but it is a concave function. Okay.
Log x is a quasi-convex function, right?
There is no relation between like measure between quasi-convex and convexity, because even concave functions can be quasi-convex and all that.
Right. I mean, the relation comes. We'll actually talk about it maybe a little later. So for certain special classes, if you start putting certain bounds on the gradients, right? We'll talk about, say, Lipschitz continuity and smoothness. So under certain conditions, the relations start emerging more strongly. But in general, all I can say is that every convex function is quasi-convex. That is the only statement we can make. Okay.
Okay.
Yeah. So yeah, all I can say at the top is every convex function is quasi-convex. It's a more general class. Now your question is how general is that class? Uh, how many functions does it have which are not convex? Well, it has many functions which are not convex, right? But under certain conditions, they may start behaving like convex functions. That's all I can say. It's by the way, it's also an area of research, and quasi-convexity has been helpful, in certain constraint optimization technique algorithms. So hopefully we get some time to talk about it in the end. Okay.
Okay.
But what's certainly interesting is quasi-convex functions do have several regions of convexity. That I think is an interesting point. Okay. Also, most quasi-convex, as you can see here, the quasi-convex functions will have regions of convexity. Several regions of convexity. That's the other thing we can say. So general, but because of the sublevel sets being convex, the function will also start behaving convex in at least some regions. That we see in this example, right? Hope this helps. Okay. Now let's try and prove that function itself is quasi-convex. Okay, so what I'm going to do is let me draw, or rather paste a painting I have made. I mean a picture I made. This takes too long to do it in the class. Okay, so here's a painting. I mean, this takes too long to make it perfectly here. Okay. So what you see here is this inverse Gaussian. I mean, with sigma square 1 is a special case. And this you can see is a classic case of a function with infinitely many sublevel sets that are convex. And it's a non-convex function. So you obviously you can't go around proving this for one or two chosen values of alpha. You need a more generic approach than showing this for some values, chosen values of alpha. How do you prove this? Anyone has attempted this? So these are all different values of alpha. You think of this as alpha equals whatever, alpha 1, alpha 2, and so on. So you want to prove it for all values of alpha. Okay, so the proof you need to make is that the function is quasi-convex. So we're just going to inspect the L alpha sublevel sets of this particular function. You can see the expression here. Now, does this make sense? Does this look convex? I mean, I'd like to remind you what we did in the case of the zero sublevel set of particular function, right? I mean, you could think of the zero sublevel set of this function as simply, this is what we had shown. This was a zero sublevel set. The x1, x2 such that x2 is less than equal to 0. This is the one shaded in pink. Okay, so we're just trying to do something similar. So please let me know if you have made some observations. We are trying to do something similar here. So the sub-level set was all convex. Now we want to do the same thing here. Anyone has worked this through? Yeah. Otherwise, it's pretty obvious in the slide here. Um, See, we note that exp minus x minus mu square is monotonically increasing for x less than mu. Okay, so this expression is monotonically increasing for x less than mu, and it is monotonically decreasing for x greater than mu. So what is this set? Right, so there's something about mu, right? Less than mu and greater than mu. It's basically it's a contiguous interval around mu. So you want this to be less than equal to minus alpha. So sorry, less than equal to alpha minus of exp minus of x minus mu square, whole thing should be less than equal to alpha, which is the same as exp minus of x minus mu square greater than equal to minus alpha. So this set, what do we expect this set to be behaving like? Can anyone plot this function? Have you tried plotting this function? So would it behave like this? So you have some alpha prime here and alpha double prime here, and here is centrally situated, I mean somewhere situated here is a mu. So it's monotonically increasing for x less than mu, right? This expression is monotonically increasing for x less than mu, which means it'll keep on increasing. So do you expect a bound to be there at alpha double prime, a lower bound? Like to you to express your thoughts, findings. What are you trying to get? You're trying to get your x for a fixed value of alpha, right? What will be the relation? I mean, where would alpha play a role here? So would you expect this alpha double prime to be a function of alpha and obviously maybe mu? Right? Those are two things here. Mu and alpha are the two things fixed here. Okay, so I would like you to think a bit more and see how you could derive alpha double prime and alpha prime in terms of alpha. But the important thing is it's contiguous. Okay, I would like you to think more on closed. I mean, is alpha double prime minus infinity, or is it? I mean, is it some finite value? Uh, that you need to think about, but it is contiguous, and therefore it's a convex set. And we did this for any alpha, so we are good to say that fx is a quasi-convex function. Okay. You can similarly prove that the negative of the multivariate normal densities is all for single dimensional case, right? But you have to generally prove that negative of the multivariate normal density function is also quasi-convex. I mean, the simplest thing for you to do would be to plot, right? And I would encourage you all to plot. But let me I've done this plotting, so let me just do this for you here. Here are multivariate normal plots. Okay, so for different values, mu is minus point. I mean, yeah, sorry, mu is 0, 0. Sigma is 1, 1, 1 diagonal, minus 0.8 along the off diagonal entries. So it's a two-dimensional case, right? So you'll see these are the sub-level sets. All of them look convex. However, the function itself is non-convex. So the function is a non-convex function because it is bell shaped. I mean, it's like this, but then it's concave rather here, but it is kind of tending to be convex in these regions. Okay, so not convex everywhere. Whereas, yeah, as you would have made a note by now, all sublevel sets appear convex. Okay. Um, we'll move on to the next topic. If you, unless you have some questions, comments. Okay, so convex functions are, I would say, a special case of quasi-convex functions. And the notion of quasi-convexity is through notion of the sublevel sets, which lies in an Rn space. Okay, so you have the function f going from R to Rn. The sets in n dimensions, as Rn basically. However, there is a notion of epigraph, only one epigraph. Okay, epigraph is a set in n plus 1 dimensions. Sublevel sets are infinite, right? Are multiple sets in n dimensions, whereas epigraph is just one set. Now, the notion of epigraph will become very important when we look at duality. Important when we look at duality, when we look at, for example, strong duality conditions, zero duality gap, and so on. But the interesting thing is epigraphs are equivalent, convex epigraphs are equivalent to convex functions. They're saying a function's epigraph is convex is the same as saying that the function is convex. Okay, so that's why they become interesting. Certainly more interesting than sublevel sets from the point of view of convexity. Okay, so let's get the definition. So epigraph is a set of points lying above the graph of the function f. And again, I'm going to resort to some drawing. I want to save time drawing. Let me do this in the next slide, and then I'll borrow some of it here. So, okay. So let's see this diagram here. Okay, so this part in green is the epigraph. What you're seeing here is the graph of the function in gray. And the part in green is the epigraph. Again, I'm repeating from the definition, it's a set of all points lying above the graph of f. So if the function is convex, then the function itself is cup shaped, right? The graph of the function is cup shaped. And what we are saying is the epigraph then looks like a convex set. So it's very intuitive when you look at this cup shaped notion. It's intuitive, especially in two dimensions, the input spaces in R2. It's even more intuitive when you look at affine functions, right? So affine functions of vectors A transpose X plus B. And what is this epigraph? Its epigraph is this xt such that A transpose X plus B is less than or equal to T, which is a half space, a convex set. So again, that's easy to see. Let me just draw it for you. Here's the half space example. So what you see here in green is again the so here you have the green, the graph of the function, the affine function, and the part in red is basically the epigraph. That's the epigraph. Okay, how do you prove that it's a convex set when the function is convex? I would say the proof is again very simple. And I just want to give you this big picture. Um, big picture is that the sublevel sets will prove to be convex only one way, one directional, right? A function is convex and the sublevel sets are convex, but we were not able to go back. Obviously, we showed a counter example. But in epigraph, you can reconstruct back. You can say if the epigraph is convex, a single one epigraph, then the function must be convex. Okay, so let me specifically show you the big picture in the next slide, which I'm putting together.
So, sir, the epigraph is a set of points, right?
It's a set of points in R in n plus 1 dimensions. As you saw here, right? It's in Rn plus 1. The subset of Rn plus 1. Yes, the sublevel sets are also sets of points, but they're in Rn.
Yes, so the alpha being the plus one nth dimension.
Exactly. So let me show this in the next slide again once more. So here you have, yeah. In fact, let me show the green part, shaded part as well. Yeah. Okay. So this green shaded part, as you pointed out, is the epigraph. And let me put together all of them in perspective. This is the epigraph of the function f. There's no notion of hypograph. It's just all the points lying below. Okay. For concave functions, hypograph becomes more interesting. And as I said, this is a subset of Rn plus 1. And this point, this curve in gray is called the graph of function f. And what I want to point out is that if you have these points x1, x2, xn, comma z. Okay. Z is the function value. This is a z axis you can see here. So if this function, if let's say this is convex, it basically if you want to say, okay, this is a representation. Say this is a point in the epigraph of f, a canonical point in the epigraph of f. And our claim is that the function f is convex if and only if its epigraph is convex. Okay, now let's look at it. Look at the sublevel set view, which is on the right hand side. What you see here is L alpha f, and this L alpha f, okay, this is basically in Rn. Okay, and we are saying that if before all alpha in R L alpha f remains convex, then f is quasi-convex, of which a special case is convex functions. Then f is called quasi-convex. That's our definition. But we proved that every convex function is quasi-convex. This is not if and only if. Okay, so every convex function is quasi-convex. Now what we want to prove is that every not only is every convex function not only is a sublevel set correspond not only the epigraph for a convex function convex, but if the epigraph is convex, then the function must be convex. That additional claim we are making. So is this picture clear? The epigraphs are all about Rn plus 1. The sublevel sets are all in this Rn space. These concentric circles, as we are seeing. And we saw in the case of Gaussian. Right? That's a non-convex function which is quasi-convex. Okay. So with this, there's a, as I said, there's a one-to-one correspondence between the convexity of function f and of the set epf. So we're saying that if D in Rn is a convex, a non-empty convex set, and f is going from the domain D to R, then what are we claiming? F, exactly what we said in the previous slide, that f is convex if and only if its epigraph is convex. Okay, I'll just use lowercase epi for consistency. So how do you prove this? Anyone? I mean, I must tell you the proofs are very simple. First, we'll try and prove that of f is convex function, epigraph f is convex set. And I must tell you the proof is very, very similar to that for sublevel sets. I mean, you just need to prove that if the if you have a convex combination of you know, the upper bounds, right? So epigraph f is what? It's all x comma z, right? It's all x comma z. So if function is convex, then you want to prove that epigraph f is convex. That means for every two convex combinations, so x1, x2, xn, z, and say x1 prime, x2 prime, xn prime, z prime. What we want to show is that let's copy this, and then what we'll have to prove is as follows. If this is true and this is also true, and the function f is convex, obviously, so I'll put a prime here. X2 prime is xn prime, zn prime is a point. Both of these are points in epigraph f. Then our claim is that theta of the first one, x1, x2, so this is a convex combination, xn z plus 1 minus theta times x1 prime, x2 prime, xn prime, z prime is a point in, is also a point in f, ef. I f. Okay, so that's the proof idea, and as I said, this is very in this last step, it's very similar to that for sublevel sets. Okay, so we've done exactly that. So I used alpha 1 instead of z1. So let me just be consistent. Instead of z prime, I can use alpha and alpha prime. Yeah, you should just get robust to change of notation. So here I have alpha alpha and alpha prime. Okay, so for alpha 1 and alpha 2, whatever. Okay, so you want to do this for any, you want to show this for any theta in 0, comma 1 open interval. And this is very simple. I mean, f of the convex combination is less than or equal to the convex combination of the functions, which is less than or equal to the convex combinations of the alpha 1s and alpha 2s, or alpha and alpha prime. Why? Because we know that this function value f, um, we know that this function fx1 is less than or equal to alpha 1, and we know that fx2 is less than or equal to alpha 2. This is simple. This is a necessary part. Sufficiency, you want to prove the other way, that if the epigraph is convex, then the function is convex. That's also very simple. So since epigraph f is convex, we know this combination, right? So which means that f of theta x1 plus 1 minus theta x2 is less than or equal to theta f of x1 plus 1 minus theta f of x2. Why? Well, I mean, x1 x1 f of x1 is an epigraph, x2 f of x2 is an epigraph, right? And we have shown that, and we know that epigraph f is convex. Therefore, this convex combination also lies in epigraph. Therefore, it must be that the f or the f of the convex combinations, which is less than or equal to the convex combination of the f's, must be less than or equal to the convex combination of the alpha 1 and alpha 2. So any questions? Okay, please let me know if you have questions. Okay, we'll proceed. So now we'll move on to first order properties. Now I will try and explain these first order properties in terms of epigraphs. Okay, the epigraphs are going to be very handy in understanding these first order properties, and let me give you a hint. The idea is that these epigraphs are going to be lower bounded or supported using hyperplanes defined by the gradients. Okay, so let me just copy this canonical image. It will be used time and again. Let me copy this here. Okay, so let me, yeah, hopefully this is clear now. So what we are saying is, if the function convex function is the same as a convex epigraph, right? So let's try and give that interpretation from the word go. We saw that convex function is equivalent convex epigraph of that function. And now what we want to do is use that property to show first order definitions of convexity. And the way we'll do that is that the convex epigraph is in Rn plus 1. The gradient will be used to construct a hyperplane in Rn plus 1, which will lower bound the epigraph. The grade we will show the gradient of a convex function any point used to construct, okay, a hyperplane at that point, and this is an Rn plus 1, which will lower bound, or what, actually more than lower, yeah, lower bound you can say, or support. I mean, it's basically lower bound the function, or equivalently support the epigraph of the function, which obviously is lying in Rn plus 1. Okay, so both are Rn plus 1. The hyperplane is in Rn plus 1. And so is the epigraph of the function. That's also in Rn plus 1. And that's exactly what we are showing. This lower bounding thing. Let me, I'll draw a better picture soon. Um, but hopefully this should, let me actually draw a better picture. So we want to show that function, okay. The picture here. And what we'll try and do is that we'll try and understand how the um, convexity is becoming very important for us to be able to draw such a lower bound. Okay, if a function is not convex, epigraph is not convex, you may not be able to draw such a lower bound. Okay, so let me just show this example. Yeah, this hopefully is clearer now. So here's the lower bound. Switch this to blue. Okay, so here you see this lower bound function x at this point x, this region in blue, right? This is being defined exactly by our hyperplane. We have actually drawn this hyperplane fx plus the gradient fx transpose y minus x, this dot product. This is this part in shaded blue, right? And if you have strict convexity, this inequality will be strict, which means that the hyperplane will lie strictly below the epigraph. Okay, I just remind you this is the epigraph. And this is a very important geometric understanding, because this will also lead us to the notion of subgradients. Somebody may wonder, what if the function is not differentiable? You can still have this notion of lower bounding using a hyperplane, okay, but not using the gradient vector. Hyperplane defined in terms of something called subgradient. So it's a very powerful understanding. And please ask if you have questions. Okay, so I've just shown this example, right? I mean, this is supporting set here. See what happens if you don't have a convex set. And if you have a if the function is non-convex. Now let's look at a point here. There a supporting hyperplane to the set at this point x. This is so these are not examples of epigraphs. I'm just saying these are examples of convex sets. This convex set, does it have a supporting hyperplane at the point x? Yes. Does this non-convex set have a supporting hyperplane at x? Would you like to answer?
No, sir. It will cut across the convex set.
Yeah, it's not going to be supporting, right? It's going to somewhere or the other just cut, as you
Yes.
pointed out. So if I try and do this, I mean, I'll try and do this. It's cutting. I mean, there's no way basically, and it has to be supporting at x, which means it's like almost touching x. I mean, you can't just draw a hyperplane like this and say it's supporting. That's not supporting, right? So this is an interesting. I mean, there's another way of understanding. All of us know what is this dot product, right? What is this dot product between the gradient and y minus x? Please answer this question. What is this dot product? We have seen this before. Does it have a notion that does it have a name in terms of derivative? Yeah, I'm going to write some sentence. You can help me
So is it
calculate.
like can be related to the direction vector that we did in the previous class?
Directional derivative.
All right.
Right. So it's saying that function at y is lower bounded by function at x, right? Plus a directional derivative at x along y minus x. Isn't that correct? So this is the yeah, this is the intuitive understanding that looking at the directional derivative at x going along y, but you're saying no, and that's like the upper bounding, right? So you're saying that this function y is above, the graph is above the function at x plus the directional derivative. That is the lower bound, right? That's also acting as a lower bound approximation. And this is also used very often. Even for non-convex functions, this property is used. Okay. Um, People often resort to this first order approximation. So this gives a first order approximation. This is the first order lower bound approximation. It is not. This gives basically. Okay. Anything else? So not only we have a notion of supporting hyperplane. This yeah, the part in blue is notion of supporting hyperplane. Let me also just point that out. Now, in the case of strict convexity, as I said, there's a strict inequality, but in the case of strong convexity, you have a gap. And what is that gap? That gap is basically a quadratic function between y and x. Like the directional derivative was a function of y minus x. Now we're looking at a quadratic function of y minus x in addition to the directional derivative. Okay, so yeah, I mean I can just take the same sentence. Okay, so same sentence. I'm now going to put it here. Here, what is happening is the function is lower bounded by function at x plus directional derivative along y minus x plus a quadratically increasing function of the norm of y minus x. Okay, so there's a little bit more gap. Actually, this is the kind of gap that helps prove several results on convergence of algorithms. I already mentioned that, but we'll use this. This property is used very extensively. Okay. Um, Convergence of algorithms, especially because this is directly involving gradient, right? Built around gradient descent or stochastic gradient descent. Okay. Anything else you want to ask on this slide? We'll otherwise move on. Okay, so the proof of this. How do you prove this? Actually, the proof of sufficiency is very similar for all the three statements, right? So we'll just prove it for one, which is for this normal convexity case. We want to prove that suppose one holds, basically that the supporting hyperplane exists or there is a lower bound for a convex function. Then we want to show that the original definition of convexity holds, right? So suppose one holds and your x1, x2 and d and any theta in between 0 and 1. So we have these two inequalities. How do you use them to prove anything? Okay, so I'll bring back this image that might help you. So we are saying we have, oh, I'm sorry, this is x1, x2 as two different points. I shouldn't use this. I shouldn't confuse you. Let me just not use this. Yeah, x1 and x2 are two different points, not coordinates here. Okay, so what's the next step? Well, this should become obvious to you. The manipulations are too many, right? So what you can do is you can multiply the first one by some scalar. Let's say, I mean, we have to see how things get cancelled out, right? So f of x1 and you have f of x2 here, and x2 minus x and x1 minus x. So typically you would have theta for the first one, right? Theta times, for example, x1 and 1 minus theta times x2. So that's what x is, right? So I would just take theta times the first 1 minus theta times the second and add them. Then what will happen? Right? You add 1 minus theta times the second to the theta times the first. What do we get? So you'll find that. Okay, let me just copy this and then quickly we'll be able to see what gets cancelled out. Here, right? So what gets cancelled out is you'll have theta x1 minus, see the gradient is with respect to x in both places. Okay, that's good for us. So theta x1 plus 1 minus theta x2, right? We'll expect some cancellation with x and that's happening, right? So we'll get cancellation of the gradient term basically. The normal inequality will get very easily. So theta f of x1 greater than equal to, plus 1 minus theta f of x2 get it greater than equal to theta f of x plus 1 minus theta f of x, which is f of x. But that f of x is nothing but theta x1 theta x1 plus 1 minus theta x2. So this is very simple. This is straightforward. Now, so this proves that fx is a convex function. Now, in the case of strict convexity, I mean, we'll have just a little bit more work to do. What is that additional work? Well, just need to show that this inequality is strict. It's not a problem, right? In the case of strict convexity, the inequality will, all inequalities remain strict. That is it. Nothing more. Okay, so that holds and follows through. Now, in the case of strong convexity, we need to do a little bit more manipulation. Okay, so all we have to do is theta f of x1 minus. Okay, so this part I'm going to leave you as homework. I don't think I'll spend the time doing it unless you have a question. Okay. So this bit of manipulation you have to do, the theta f of x1 minus c by 2 norm x square plus 1 minus theta f of x2 c by 2 norm x2 square is greater than or equal to f of x minus c by 2 norm x square. Okay. So this part is homework, but I will discuss only if you ask me. Otherwise, it's a simple manipulation. By the way, I forgot to mention these derivations are all there in my detailed convex optimization notes. I've been putting references for every class, so you can also feel free to refer to them. Okay, so this should be simple. Necessity. See, necessity is the trickier part. And I'll tell you why. Because now we want to go from the plain case to a derivative case. Okay, so that's why we have to invoke the definition of derivatives. And it'd be nice to also show what's really happening, right? Again, I want to stick this image here. This might help. Well, though I don't want to use this x1, x2. So yeah, just don't use the notion of x1, x2 here, because these x1, x2 are coordinates, right? So if you want, I'll just rename these to something else. Okay, so we'll call them. I'll say x. Yeah, let's just use x1 comma x2. These are actually indices. So I'll just use this simpler notation. With this understanding, I mean, let's go back to what this dot product was. This dot product was a directional derivative. Okay, we did that in the previous slide. So this is nothing but the directional derivative. Okay, and then you can write down the expansion of directional derivative. What is it? It's basically in terms of limit. Limit as something tends to 0, right? Okay, and that's what we see in this here. So this is directional derivative is basically about limit as uh, as you go from x1. So before I move to the next slide, think of the following. So you have this point x here, and let's say I go from this point x to a point I don't want to use y. Okay, let me use y. It's okay. I'll remove this. Oh yeah, this is y. Let's say I'll use y. That's fine. So you have y here, and I want to go from x to y. So x2 minus x1 can be also thought of as x. Sorry, this derivative gradient at x1 could be thought as the difference between the function values at x plus a theta times x2 minus x1, or a theta times y minus x. Okay, so what we are looking at is this direction, looking at f of x plus theta times y minus x. Okay, replace x with x1 and y with x2 minus f of x. This whole thing divided by theta is what this line is representing in the direction of y minus x. Okay, this hyperplane. The value. Okay, so this is a magnitude, rather magnitude. This particular expression where along the direction y minus x. Okay, so this is what we need to get. Okay, this is with um, theta tending to 0. So I can put a limit as theta tending to 0 here. Okay, so that is what I should expand it as. limit as theta tends to 0. Now in this case we have x1 plus theta, x2 minus x1. So I just used x1 in place of x and x2 in place of y. So this is clear. Now what about this? This is okay. Now again the same algebraic trick. You'll use rearrange terms. Look at this expression and this expression. You can try and derive one from the other, right? So this, what is this less than equal to? Anyone? So you take f of x1, sorry, f of theta x2 plus 1 minus theta x1, which is the same. This is exactly the same as this expression. We are just seeing this expression differently. I'm saying x1 plus theta 2 well, plus theta times x2 minus x1, the same. Okay, ditto. These are the same expressions. And we are trying to get f of x1 on the left hand side minus f of x1. So I'll basically get a term corresponding to this one, f of x1. I'll bring it to the left hand side. So what remains on the right hand side is theta times f of x2 minus f of x1, right? But then limit as theta tends to 0. So I have to put this, or I will do all of that. So I have to say this divided by theta. Let me just this is limit as theta tends to 0 of this entire expression. And what is that? This theta is not 0, it's tending to 0. So you can actually cancel out theta from numerator and denominator and basically get f of x2 minus f of x1. F of x2 minus f of x1. That's it. And this expression is exactly what we cared for. I mean, just put together the extreme left hand side and the extreme right hand side and the inequality. We are done. Right? This proves our expression. First order definition of convexity. So necessity proofs for 2 and 3 are very similar. The strict inequality is not preserved when we take limits. Okay, so the strict inequality is not preserved when we take limits. This is very important. Now we'll have to work a little hard for this. The tricky case is not strong convexity but strict convexity. Okay, let me just highlight this. Take limits. So when we take the limits here, the previous slide when I said okay, limit theta tends to 0, I just boldly put this less than equal to, right? Because it was a less than equal to. But if the original inequality was strict, then after taking limits, you won't have strict inequality. Okay. So let me note that inequality does not remain strict when we take limits. That's a bit of a problem, this proof technique, but then we will try and fix it. So that's exactly we discussed. So we address strict inequality through a counter example. So basically counter argument, right? We are saying that, well, let's say there was equality. Okay, instead of saying oh it's a strict inequality, since limits leads to a less than equal to, we say let's assume that there was a strict equality. Then what happens? F of x2 is equal to f of x1 plus this dot product between gradient f at x1 and x2 minus x1 for some x2 not equal to x1. And we show that this actually leads to a contradiction. Okay. So the next step would be show that this leads to a contradiction. What's the contradiction? Anyone wants to guess? Yeah, please do participate. It will be helpful. So it's a little tricky. I mean, the proof is a little verbose. Okay. So if f is strictly convex, we can actually write this inequality theta if theta x1 plus 1 minus theta x2 of f is less than theta f of x1 plus 1 minus theta f of x2. This is from strict inequality. Okay, and then if you have equality at x2, so x2 is not equal to x1. Okay, it's very important to note. I mean, if they were the same, then there's nothing to do. The chapter is closed. X2 is not equal to x1, and this is where we're saying that this, along with x2 not equal to x1, is going to lead to a contradiction for a strictly convex function. Okay. So then we say, yeah, I'll basically take this convex combination of x1 and x2 and show this inequality. Yeah, and a little bit of manipulation. So we basically use what we had proved. When we say previous two expressions, we are also using the first order definition of convexity, not strict convexity. So the first order definition, which we already proved, right, of convexity, or say ordinary convexity, to distinguish it from strict convexity. So we are going to just use that, and that leads to a contradiction that f of x2 plus theta transpose fx2 x minus x2 is less than the same expression. So the two are basically going to contradict each other. So we are saying that the same expression is less than the same expression, which cannot hold for any x1 not equal to x2. Okay, so this, yeah, I mean, for strong convexity, again, you can show that gx is fx minus c by 2x is convex, and then we'll just apply the first definition to G. Okay, so that basically the no ordinary convexity to G. Okay, so I think we are done with these. I'm not going to delve unless you ask. Okay, so this is a complete statement. At any point, the linear approximation based on a local derivative is going to give you a lower estimate of the function. That's the convex function always lies above the supporting hyperplane at that point. And again, I want to go back to this image, which is the more generic two-dimensional case. In case you struggle with the one-dimensional, how it generalizes, here's a two-dimensional case, which is yeah. It should be helpful as well. Okay, so if you are clear, then we'll move on to the second order definitions. Any questions at this point? I'll just take a pause. If there are none, then we'll move on to the second order definition. So we recall the Hessian of a continuous function. Now we are already familiar with something in the one-dimensional case. We already used that, in fact, for talking about convexity of the or non-convexity of the negative of the univariate Gaussian. But let's take an example. We will take some more examples going beyond those. if I take the log sum x, how do you prove that it is convex? Well, we did it by first principles. Can we use a Hessian to prove that log sum x is convex? Okay. And the answer is yes. Okay. It requires, of course, a little bit more work, and in fact, you'll find some. I think probably Boyd. Okay, Boyd's convex optimization book uses the fact that the Hessian of the function must be non or other positive semi-definite, or Hessian being positive definite. This is a necessary and sufficient condition. So what we did, we had a slightly different way, right? We used at the midpoint convexity and then used Cauchy-Schwarz inequality. We found that none of the basic properties, the composition were helpful. So we had to go back to some first principles and some other tricks. But you could also use a Hessian, right? And that's exactly what is being highlighted here. So you can show that this positive semi-definiteness, which is denoted by this greater than equal to 0 on the Hessian part, that's a necessary and sufficient condition. It's if and only if. Now writing the Hessian is going to be not very easy always. Now we all know what the Hessian for. So since we're talking about log sum x, let's start with the simplest example. Exp. For exp of x, what is the double derivative? Anyone? This is yes. Someone was trying to say
It's the same.
is the same
E
expression,
for x. Yeah.
right? Exp of x. Okay, so now suppose I give you. So I'm trying to go slowly, right? So suppose I give you now, okay, sum of exps. Okay. So instead of going to log sum, let's look at sum exp. Okay, sum exp. Summation I exp of xi. Then what is the double derivative of sum exp? Or what do I talk about? I can't talk about double derivative. Obviously, there are multiple xi's. I can talk of the Hessian. What is this Hessian going to look like? Yes. Are there any mixed partial derivatives? Partial
No, sir.
derivative, all of them are zero, right?
0.
So what would it look like? A diagonal matrix with xi, right? And everything else is zero. Okay, so this is how you can derive. Now, what about log sum exp? So sum exp is fine, but log sum exp, what would happen? Anyone? How would the expression look like for the Hessian? Yes, try and work it out. It's okay if you're taking some time. Okay, so I mean, one possibility is you draw the Hessian, right? But let me give you a simpler example, a simpler proof. You can actually write down the Hessian. That's possible. But instead of writing down the Hessian, let me give you a different proof methodology. Ultimately, you have to show that the Hessian is positive semi-definite. What's the definition of positive semi-definiteness? What does this expand to? This is if and only if? Yes.
Like the eigenvalues are all non-negative.
Eigenvalues are all non-negative, or is there another equivalent definition?
The X transpose matrix X has to be greater than or equal to 0.
Let me use V transpose because X is the argument here, right?
Yeah, right.
For all V, we'll have V transpose Hessian at a fixed point X. V transpose or V transpose
greater than equal to 0.
Yeah, greater than equal to 0. So my question is, can we now look at this expression directly? Right? We want to show this is positive for all values of V. Can I not do that for the case of log sum X? I mean, by the way, this has a name. What is this? What is this denoting? This denotes what? This is basically curvature. Okay. So this entire expression is a curvature expression. And we are saying that along any direction V that you take, the curvature should be positive. So that's that's an important point, right? So let me again, drawing it is going to take some time. Okay, so what we are going to do is we look at a slice of the function. Okay, this is a little tricky. Drawing it is going to be tricky, but let me try anyways. This is my function, and we are saying that there is a slice here. Any slice that I take, that slice is basically the slice of the function based on direction V must be curved upwards. That's what we are saying. Okay. So direction V here, if I take a slice of the function based on the direction V, this V you see here must be curved upwards. Any direction, it's not one specific direction, any direction V must be curved upwards. Which makes sense because that helps us relate to the one-dimensional case again. Okay, so that's it for the for this interpretation. But in terms of actual proof methodology, how can I use it? Right. So the intuition is for first order condition, we require that the directional derivative is non-decreasing in every direction, right? Here we are saying that the curvature is positive in every direction. Okay, so that point is fine. But now I want to use it. I would like you to suggest how to use this for showing that log sum x is. Okay, so I'm going to leave this. Yeah, why don't you suggest? I've given you more hint to show that log sum x is convex. Can we prove that the quadratic expression is always non-negative. About the quadratic expression on the right, and the intuition is, again I'm recalling the intuition. Yeah, but as you work out, anyone? If you're able to work out, let me know. Did anyone manage to write this expression? Hello, some response? Okay, so I'm going to leave it as homework if you are not able to solve it now. I think the hints have been already provided. It's a very simple, straightforward idea. All we have to do. So I'm just going to start it off and then leave it. This should be certainly done by you. Um, so I want you to, I would like you to just write down this expression for one. Just write down the V transpose. Okay, but instead of writing down the Hessian, I'm just going to immediately expand it. Okay, this expression. Or if you want to be more specific, the Hessian of the log sum x, right? Whose convexity we proved in a different manner earlier. I'm going to use a different expression. Okay, so you'll find that it has a very interesting pattern. And we'll move on to the next topic. Okay, so this brings us to the next topic. Oh, by the way, I have in the convex optimization notes, I provide derivation or expressions for other types of functions. Log sum it's all is there, but I also provide expression for say negative geometric mean, for quadratic over linear, for general quadratic expression. So yeah, I think on page 67 of the convex optimization notes, a table of Hessian. You can actually look at that, right? So that might give you an idea. Hessian for some convex optimization problems. You can find them there. Okay, yeah, I think can just put this link here. Somehow, okay, it's not showing up. Um, but I can give you this idea right away. This is how it looks like. So here's an example of different quadratic functions. So log sum x has this. You'll find this expression Hessian, right? But what's more interesting is what that quadratic expression turns out to be. That's that you'll probably resonate well with whatever we have discussed so far, even with Cauchy-Schwarz inequality. So just do that. It'll kind of help close the loop. Yeah, so I would like you to just focus on this one. The others you can see for quadratic, it's like and quadratic over linear. These are very simple expressions. Oh, sorry, this is A. There's a mistake here. It's A. So yeah, I'm trying to draw your attention to this expression. Okay, let's move on. If there are questions, please let me know. So this moves, I mean, helps us move to the next topic, which is subgradient. So to say that a function is differentiable is basically to say that there is a supporting hyperplane or a linear tangent that estimates the function, right? But if the function is convex but not differentiable, can we have a similar notion? And it turns out that the answer is yes. Um, so again, let me show this example. This is what we've been showing so far, right? This is the gradient f minus 1. That's exactly the um, hyperplane at this point. But imagine that the point was the function was not differentiable at this point. It had some kink. You can see this point there's the function has a kink. Can we still have a supporting hyperplane? Okay, so answer turns out to be yes. That you can have even at non-different points of non-differentiability supporting hyperplanes. And that is the notion of subgradient. I'm just going to show this for the hinge loss, or you may any basically any loss, right? Which is convex, okay, but not differentiable. But let's look at this case. This function is convex, okay, but at this point, what do I do? Well, my suggestion is think of a cone consisting of the perpendicular to both of these. All of these will help you define hyperplanes. Okay, the hyperplanes, corresponding hyperplanes are going to be, one is this and the other is this. So everything in between these two. All of these, basically these hyperplanes. These are the normals I've shown here. These are the hyperplanes. So intuitive idea is that all of these hyperplanes are supporting. So at this point, let's call it T of non-differentiability. Of this convex function is a convex function. There seem to exist several supporting hyperplanes. And their corresponding normals. Each supporting hyperplane can be defined in terms of a normal. Okay, and so this point I've given it a name. Sorry, I didn't mention it here, but let me do that. This is my point T. So we are saying that, well, we can, why not use this notion to define the so-called subgradient, right? So this is this notion of subgradient. There's my multiple linear tangents. I've now shown this for arbitrary convex, but a convex function which is not differentiable everywhere. I've said that, well, there could be this H which could belong to this large space, lots of and specifically again here I'll just draw H would actually be corresponding to all these normals. Okay, so all of these, this space, there could be a whole bunch of H sitting here, which give you a corresponding notion of hyperplanes. These all these hyperplanes. Okay, these are all subgradients. Then a subgradient is any H such that f of y is greater than or equal to f of x plus h transpose y minus x, or in other words, h comma minus 1, h defines a supporting hyperplane at x. Okay, any questions? Okay, so the fact that for any convex set there is a supporting hyperplane I'm not getting to those. I have an entire course on convex optimization where a lot of very involved proofs are there. So any convex set has supporting hyperplane at any point on its boundary. We have now going more by the intuition so that we can move fast to algorithms. So probably in a lecture or so we'll be doing algorithms and their convergence. Okay. Um, any questions, or we'll conclude for now?
So, sir, like instead of a single tangent, we are saying that there is a possibility of a set of infinite tangents.
Right. Right. There are infinite tangents unless the function is differentiable at that point, in which case, well, as you can guess, that single tangent will correspond to the one coming from the gradient.
Yes, sir.
Okay, that's the intuition. Okay, probably end the call now. Thanks.